All right, one more video in this section on applied optimization where we focus on business applications. In the last video, our end goal was to maximize profit, but we got there kind of a long way by looking at cost functions and looking at revenue functions. And the revenue function in particular was very simple. We just assumed that we were selling things for $200 each, so the amount of revenue we get is just 200 times the amount we sell. But maybe a less oversimplified example would be worth looking into. Because in reality, you probably don't have a fixed price. You're probably trying to figure out what the price should be. And if you make your price a little bit less, you're going to sell more. And if you make your price a little bit more, you're probably going to sell less. So that's the kind of example we're going to examine in this video. It's still going to be a little bit oversimplified. We're going to assume that the demand is linear, which may not be a fair assumption. But with the mathematical tools we have available, this is the best that we can do. So what we're going to do is we're going to come up with a demand function. What a demand function does is it relates together the price and the quantity. The price of something that you're selling and the quantity of sales that you make. And sometimes your demand function will just be given to you, and sometimes you'll be asked to determine the demand function using historical data. And that's not as bad as maybe you'd think. I think the easiest way to think about it is create X and Y axes, but on the X axis put the price, and on the Y axis put the quantity. When I charge $10, in other words, when P equals 10, I sell 200 units, so Q equals 200. So think X is 10, Y is 200. Maybe here's 10, and here's 200. I have this point right here on my demand curve. However, when I change the price, when I increase it from $10 to $20, I sell less. That makes sense. Instead of selling 200, I'd only sell 120. So when my price is over here at 20, my quantity falls all the way down here to 120. These 2 points are on our demand curve. And since we're told to assume that demand is linear, we can connect those 2 points with a straight line. Note that if we weren't making this assumption, this curve might be much more complicated. What we need to know is the equation of this curve. Well, it's a line, so think y equals mx plus b, except instead of y's, we're using the letter q. And instead of x's, we're using the letter p. So the 2 parameters that we need are m and b. M represents the slope. When you're thinking about m, you might be thinking the change in the y coordinates divided by the change in the x coordinates. But in the language of this problem, it would be the change in the q coordinates divided by the change in the p coordinates. So maybe I call this P1 and this Q1, in which case I'm calling this P2 and this Q2. Plugging in all those numbers, in the top I got 120 minus 200, and down in the bottom I got 20 minus 10. I've got negative 80 divided by 10. It looks like my slope is negative 8. Now that I know the slope, I can use the slope and 1 point to come up with the equation. Maybe think y minus y1 equals m times x minus x1. I'll switch colors so this doesn't all run together. However, in this specific example, they're not y's and x's. Remember, the y's are the q's and the x's are the p's. So it would be q minus q1 equals m times p minus p1. We figured out that m was negative 8. And if we plug in 10 and 200 for P1 and Q1 respectively, we get a P minus 10 over on this side and a Q minus 200 over on this side. This is an equation that relates together the quantity and the price. However, often we want to solve for one variable in terms of the other one. And if we want quantity as a function of price, we better solve for Q. So I got Q minus 200 equals, if I take this negative 8 and distribute it through the parentheses, negative 8P plus 80. And then if I add 200 to both sides, I get Q equals negative 8P plus 280. Oh yeah, that makes sense. If I extended this line, it looks like the y-intercept would be about 280, and I'd go down 8 each time I went 1 unit to the right. In other words, I'd sell 8 less units each time I increased the price by $1, or I'd sell 80 less units when I increased the price by $10. If I'm asked to determine quantity as a function of price, maybe I would write Q of P is equal to negative 8P plus 280. This is what's called a demand function. It's telling you the quantity that's demanded for any price that you charge. Using this demand function and the fact that revenue is just price times quantity, I can come up with a revenue function. And if I want that revenue function to be a function of price, it would be R of P is equal to quantity times price, but quantity is this mess. So instead of writing Q times P, I can write negative 8P plus 280 times P. Revenue is price times quantity. Here's the price, here's the quantity. Now that we have a revenue function, we might be asked to maximize the revenue. When you're asked to maximize something, think optimization, think you're going to need to take the derivative. If you're going to take the derivative, it might make sense to go one step further up here to simplify and rewrite this as negative 8P squared plus 280P. Get rid of these parentheses so that you don't have to use a product rule. Maximize the revenue by taking the derivative of the revenue function, r prime of p. That would be negative 16p plus 280. Then look for critical values by taking r prime of p and setting it equal to 0. Negative 16p plus 280 equals 0. Add 16p to both sides, and we get critical values when 16p equals 280. In other words, p is equal to 280 divided by 16. The top and the bottom are both divisible by 4 at least, because 28 is 4 sevens. So we could rewrite this as 70 over 4, or I guess even 35 over 2 if we recognize that these are both even. We have a critical value at 35 halves, in other words, 17 and a half. In other words, a critical value when we decide to charge $17.50 per unit. In theory, that price could be a local minimum or a local maximum. However, I'm not trying to trick you. So that critical value is going to end up being a local maximum. But for my own benefit as much as anything, I'm going to take a look at the second derivative of revenue as a function of price by taking the derivative of this thing, negative 16, and then I'm going to evaluate that second derivative at my critical value, 17.5. By changing all the p's into 17.5s, I get negative 16. What that means is my revenue function is concave down when my price is $17.50. And if it's concave down, it kind of looks like this. And if I'm at a critical value, that means that I have a local maximum. This question asks me to maximize revenue, which is a bit ambiguous. If it asks, what price should I charge to maximize revenue? I'd say $17.50. If it asks, what's the maximum amount of revenue that you could make? Then I'd be like, well, the revenue for any price is just equal to negative 8p squared plus 280p. So the revenue when I charge $17.50, in other words, 35 halves, would be equal to negative 8 times 35 halves squared plus 280 times 35 halves. Is that something I can simplify without a calculator? Maybe, although I don't know if you'd want to. 2 squared is 4, and that 4 in this negative 8 can turn into a negative 2. So I get negative 2 times whatever 35 squared is equal to over here. And then I can take this 280 and this 2 and reduce that to 140 times 35, whatever that's equal to. This is still more arithmetic than I want to do, but maybe I could factor a 35 out from both terms, and what I'd be left with over here is negative 2 times 35, and what I'd be left with over here is 140. Negative 2 times 35 is negative 70, and negative 70 plus 140 is positive 70. So the maximum amount of revenue that I could make is whatever 35 times 70 is equal to. You don't have to do this in your head, but if you divide each of these by 10, I get 3.5 and 7. 7 times 7 is 49, and 3.5 is half of 7. So my answer would be half of 49, which is 24.5. But then I got to remember that I divided both of these by 10s. So 35 times 70 is 24.5 times 10 times 10, or 2,450. That's just me being lazy and not wanting to use a calculator. Probably back at this step, you should use a calculator, and hopefully if I did all that arithmetic right, you'd get 2,450 as your answer. If I charge $17.50, I will maximize my revenue, and the amount of revenue that I'll make will be $2,450. And I can make different amounts of revenue if I want by charging different prices, but none of those amounts of revenue will be as much as I come up with here. All right, before we call this good, I want to make the observation that typically you don't want to maximize revenue, you want to maximize profit. So really, we shouldn't maximize this function, we should maximize our profit function. But that's going to be a little bit challenging because we're not given a cost function, we're just given the information to figure out a cost function. We're told that our costs are $5 variable and $100 fixed. What that means is our cost, if we sell Q units, is $100 our fixed cost, plus another $5 for each unit, for each Q. Our cost as a function of Q is 100 plus 5Q. And you're like, oh, I got it from here. Profit is just revenue minus cost. I'm like, yeah, that's exactly right, but there's a problem. Our revenue function had the variable price, whereas our cost function has the variable quantity. I have to make sure I'm using the same variable. So what I got to do is either change these Q's into P's or change these P's into Q's. It doesn't matter which way. I think it makes the most sense to try to maximize profit by figuring out how much you should charge, not by figuring out how much you should sell. So for that reason, I want my variable to be a P and not a Q. So I'm going to change these Q's into P's. I'm going to say my cost function as a function of price would be 100 plus 5 times. And then instead of writing the letter Q right here, I'm going to come up here to my demand function and recognize that Q is just negative 8P plus 280. From this information, I was able to write a cost function in terms of quantity, but from what I already figured out, I was able to rewrite that cost function in terms of price. Now that I have cost in terms of price and I already have revenue in terms of price, I can write profit in terms of price as this expression, the revenue, negative 8P squared plus 280P, minus the cost, 100 plus 5 times negative 8P plus 280. Note that our cost function has multiple terms, so make sure you subtract all those terms by writing these parentheses right here. Maybe I can clean this up a little bit. My profit as a function of price is equal to negative 8P squared, and then I have 280P here, but if I take this 5 and distribute it through, I'd have negative 40P here, but I want to subtract that negative 40. So I get 280P plus another 40P, I get 320P. And then if I look for my constants, this 5 times this 280 is 1,400, but then I have to add to that 1,400 this 100, so I get 1,500. My profit function as a function of price is negative 8P squared plus 320P plus 1,500. If I want to maximize profit, I better go looking for critical values. To find critical values, I got to take the first derivative. The first derivative is negative 16P plus 320. When my first derivative equals 0, I got 0 equals negative 16P plus 320. So if I add 16P to both sides, I got 16P equals 320. Divide both sides by 16, and we get P is equal to 20. If we want to maximize our profit, we should charge $20 per unit. Note that that's higher than the $17.50 that we should charge if we're trying to maximize revenue. We got to charge a little bit more to kind of make up for the costs if you want to think about it that way. You're probably a little bit overwhelmed with all this. There's a lot of vocabulary floating around, and you're probably not at all interested in me saying there's a different way you could have done this problem. However, there's a different way you could have done this problem. Recall that profit is maximized when marginal revenue equals marginal cost. That's something we proved at the end of the last video up here that maybe you've heard in a business class before. Figuring out when marginal revenue equals marginal cost is mathematically equivalent to solving for these critical values. So I should get the exact same answer either way. To figure out marginal revenue, I take my revenue function up here and I figure out its derivative. The marginal revenue is R prime, which in this case would be negative 16P plus 280, the derivative of this negative 8P squared plus 280P. The marginal costs would be the derivative of the cost function. The cost function with price as the variable is given right here. I could clean this up a little bit if I wanted, but I'm not even going to bother. The derivative of the sum of two terms is the sum of the derivatives. The derivative of the 100 is just 0. So really I just need the derivative of this term. I got this constant of 5 out in front, and then I want to multiply that by the derivative of these parentheses. I have two terms inside the parentheses. The derivative of the 280 is just 0, and the derivative of the negative 8P is just negative 8. So my marginal costs are just equal to negative 40. Profit is maximized when marginal revenue equals marginal cost. Marginal revenue is 16P plus 280. Marginal cost is negative 40. So when negative 16P plus 280 equals negative 40, I should be maximizing my profit. Let's see, add the 16P over to this side, add the 40 over to this side, and I get 320 equals 16P. I divide both sides by 16, and I again get that P is equal to 20. Profit is maximized when marginal revenue equals marginal costs. Figuring out when marginal revenue equals marginal cost is mathematically equivalent to figuring out your critical values. In either case, in this example, we saw that the price that we should charge is $20 per unit. If you're curious how many units you could sell, all you got to do is take your demand function and change all the P's into 20s. Let's see, negative 160 plus 280 looks like we'd sell 120 units. 120 units at a price of $20 each would be revenue of $2,400. Note, that's less than the revenue that we made over here, because over here we were trying to maximize the revenue that we're making. Over here we're trying to maximize the profit that we're making. By changing the price, we've actually made less revenue, but more profit because we're taking into account the costs. Wow, that's a lot. Hopefully you had a decent background in business before you watched any of these, because otherwise I imagine this was pretty overwhelming.